Now that we've gotten comfortable with finding Laplace transforms and inverse Laplace transforms, we're ready to actually solve differential equations with these Laplace transforms. And that's our question. How do we solve differential equations with Laplace transforms? And before we can, the one last thing we have to look at is finding the Laplace transform of a derivative. So let's do that. Let's find the Laplace transform of f prime of t, which by definition is the integral from 0 to infinity of e to the negative st f prime of t dt. Well, we can integrate this if we use integration by parts, where we let the u equal e to the negative st. du is then negative s e to the negative st dt. And the dv is going to be the other stuff, the f prime of t dt, which if we integrate, we can see that v then is just f of t. So put that together, we have u times v e to the negative st times f of t, and that's going to be integrated from 0 to infinity, minus the integral of v du. Well, I can pull out the negative s as a constant, making it plus s, times the integral from 0 to infinity of e to the negative st times f of t dt, which is really nice because that integral is the Laplace transform of the regular function f of t, no longer talking about the derivative. So what I'm going to do is I'm going to evaluate this guy. First, on the left side, plugging infinity in, we get e to the negative infinity, which is 0, minus e to the 0 is 1, times f of 0, plus s times the Laplace transform of the f of t, which we can represent with a capital F of t. And usually we'll change the order of this, putting the positive first, but this is essentially what the Laplace transform of a derivative turns out to be. Which means we can summarize this as a theorem or a property that if the Laplace transform of lowercase f of t is equal to our capital F of s, then the Laplace transform of f prime of t will be equal to our s times the Laplace transform of f minus f of 0. And we can extend this pattern to the second derivative by saying the Laplace transform of f prime prime of t is equal to s squared times the Laplace transform f of s minus s times the function f of 0 minus f prime of 0. And you can kind of see a pattern starting to form. If we were to do the Laplace transform of the third derivative of f of t, we would say, notice the exponent matches the derivative, so it would be s cubed times the f of s minus, and then the exponent starts counting down, s squared times f of 0, and then the derivatives start counting up, s to the first times f prime of 0 minus f prime prime of 0. So we can generate our property for the Laplace transform of the nth derivative of t as being s to the n, capital F of s, minus s to the n minus 1, f of 0, minus s to the n minus 2, f prime of 0, minus, and continue on with the pattern until we finally end up with s to the n minus 2 derivative, evaluated at 0, minus f of the n minus 1 derivative evaluated at 0. Now, usually we're going to use just the first and the second one, so those especially you should be very familiar with. And after doing a couple of these, you'll get really good at just pulling those out. As we look to evaluate differential equations by taking the Laplace transform of both sides. Let's take a look at an example. Let's do y prime prime minus y prime minus 6y equals 0, where we're given initial conditions that y of 0 is equal to 2 and y prime at 0 is equal to negative 1. We could solve this as a linear equation with constant coefficients. We know how to do that. But we're focusing on this new process of Laplace transforms. So let's take the Laplace transform of both sides of this equation. Then we would have the Laplace transform of y prime prime minus the Laplace transform of y prime minus 6 times the Laplace transform of y equals the Laplace transform of 0. Well, we just derived formulas for each of these derivatives. The Laplace transform of y prime prime, since it's a second derivative, we'll say s squared times capital Y, meaning it's Laplace transform. Capitals mean it's been transformed. Minus lowercase s times y of 0 minus y prime of 0. Then we're going to subtract. Be careful with our signs here. We're going to have to subtract, distribute a negative through the y prime formula. But we're going to subtract. The Laplace transform of y prime is s times capital Y minus a negative, which makes it now a plus y of 0. Then we have minus 6 times the Laplace transform of y, which is just capital Y, equals the Laplace transform of 0 is just 0. And we haven't really talked about that property yet, but it's pretty intuitive when you use the definition and you plug 0 into the integral, that you're going to get 0. A little simplifying to clean up because we actually know what y of 0 is and y prime of 0. Those are given to us. So we have s squared y minus y of 0 is 2, so we'll say 2s, minus y prime of 0 is a negative 1 plus 1, minus s of y plus y of 0 is 2 minus 6y. And now what we've done is we've transformed our differential equation into an algebraic equation. We can solve this algebraic equation for y. Factoring the capital Y out of all the terms with a capital Y in it, we would have s squared minus s minus 6. Then we're going to shoot all the other terms to the other side of the equation, which is going to give us a positive 2s. Subtract 1 and subtract 2 gives us a minus 3. Well, we can solve for y then by dividing by what's in front of it, giving us 2s minus 3 divided by. I'm going to also factor our s squared minus x minus 6 while we're here. So it's going to be s minus 3 times s minus or plus 2. Now that we've solved for y in the world of algebra, we're just going to change it back to the differential equation world using the inverse Laplace transform. We know we can do this with partial fractions. We're going to say it's equal to a over s minus 3 plus b over s plus 2. And then we can easily do the inverse Laplace transform. Using our partial fractions, I'm going to move over here to the side where I've got some white space. We have got 2s minus 3 is equal to a times the s plus 2 plus the b times the s minus 3. And we can solve this quickly by first making s equal to 3. 6 minus 3 is 3 equals 5a. So a is equal to 3/5. And if we let s equal -2, we have -4 minus 3 is -7 equals -5b. So b is equal to 7/5, which means our y is equal to a, we'll put the 3/5 out front, times 1 over s minus 3, plus b, which is 7/5 out front, times 1 over s plus 2. To figure out our solution, we can do the inverse Laplace transform of both sides. The inverse Laplace transform of capital Y is lowercase y times 3/5 times the inverse Laplace transform of 1 over s minus 3 is e to the 3t, plus 7/5 times the inverse Laplace transform of 1 over s plus 2 is e to the -2t. And now we have solved the differential equation by using the Laplace transform to make it into an algebra problem that we already know how to solve. What's nice about this is if we had solved it like we had our previous problems, where we treated it like a linear homogeneous equation, second ordered with constant coefficients, we would have had to go back and solve for our C1 and C2. The Laplace transform actually gave us our C1 and C2 of 3/5 and 7/5 as we worked out the problem. Let's take another example. Let's do y prime prime plus 4y equals the sine of 3t. We need to give it some initial conditions. Let's pick some nice ones. How about y of 0 equals 0 and y prime of 0 equals 0? So that when we take the Laplace transform of both sides, we first need the Laplace transform of y prime prime. We know that's s squared times capital Y minus s times y of 0 minus y prime at 0 plus 4 times the Laplace transform of y is just capital Y equals the Laplace transform of the sine of 3t. Well, we know the Laplace transform of the sine of 3t is the constant 3 over s squared plus the constant squared. 3 squared is 9. Plugging in then our y prime of 0 and our y of 0, both of them equaling 0, makes those terms go away. That's real nice. Gives us s squared y plus 4y equals 3 over s squared plus 9. Now we can solve the resulting algebraic equation. Factor out the y to get s squared plus 4 equals 3 over s squared plus 9. Divide to get y is equal to 3 over s squared plus 9 times s squared plus 4. Now we're going to use partial fractions to split this up so that we can go to the inverse Laplace transform and find our actual solution. This one's going to take a little bit more because we have irreducible quadratics, so we have to do the as plus b over s squared plus 9 plus cs plus d over s squared plus 4. And I'm going to come up here where I've got a little white space so that we have 3 equals as plus b times s squared plus 4 plus cs plus d times s squared plus 9. Not going to be able to clear anything out, so let's go ahead and multiply everything out, giving us as cubed bs squared plus 4as plus 4b plus cs cubed ds squared plus 9cs plus 9d. All right, grouping our common stuff together, looking first at our cubes, we have 0 on the left equals a plus c Looking at our squareds, we have 0 on the left equals b plus d. Looking at our s's, we have 0 on the left, giving us 4a plus 9c. And now our constants, we finally have a number on the left. 3 is equal to 4b plus 9d. Which is really nice on those left two equations with a and c. If they both equal to 0, then we know a equals 0 and c equals 0. It's the only possible solution there. The left side, we're going to multiply both sides by -4 to get 0 equals -4b minus 4d. So we have 3 equals 5d. Which means that d is equal to 3/5. And if we know d plus b is equal to 0, b must be the opposite, which is -3/5. So we can split up y to be equal to a, which is 0, plus b, which is a -3/5, times 1 over s squared plus 9, plus c, which is 0, times d, which is a +3/5, times 1 over s squared plus 4. Now that we've broken it up, we're ready to convert it back with the inverse Laplace transform on both sides. To do the inverse Laplace transform, though, you'll notice our fractions are almost like the sign of kt, 3t and 2t in this case. We just need to multiply our numerators by the square root of the denominator. So the first fraction gets multiplied by a 3, which means we have to have a divide by 3, which is nice because that reduces to -1/5. The second fraction needs to be multiplied by 2 and divided by 2. And then when I do, I get lowercase y. My solution is -1/5 times the sine of 3t plus 3/10 times the sine of 2t. And we now have our solution to the differential equation. So Laplace transforms are a real slick trick. They solve for the coefficients. They solve for the complementary and the particular. But they're also going to allow us to solve equations that wouldn't be able to solve as easily with our prior methods. Most of the problems we're going to work with today as we learn this process are going to be familiar equations, but this process can be extended to many other different types of equations, which is really nice. So now it's your turn to practice. Go ahead and take a look at those, and good luck as you work on Laplace transforms.